All right, it's here. Let's talk about moles. Uh, Not mole the animal, but remember mole the SI unit for amount of stuff. Okay, we're going to be using moles a lot during the semester, so let's kind of get this under our belt and get some good vibes going. Okay. Um, anyway, you already know how to deal with this. I just have to remind us that we know how to do this. Okay. That might sound weird, but you'll see what I mean. Okay, because we know what a dozen is, right? If I ask you in class what a dozen is, you're going to tell me it's 12 things, right? A dozen roses, a dozen eggs, a dozen donuts, a dozen whatever. It doesn't matter what it is. A dozen is a dozen is a dozen, and it's always 12 of whatever it is. A dozen dogs is 12 dogs. A dozen pens is 12 pens. A dozen kids is 12 kids. That's too many kids. Anyway, you get what I'm going for. A dozen is 12. We call this a counting unit. Okay. Well, a mole is the same idea. It's a counting unit. It's for counting small things. Okay. So let's look at this. Okay. A mole is a counting unit. This was come up with, defined by Amadeo Avogadro. And so we have Avogadro's number uh, of things. Okay. So one mole contains exactly the same number of items as there are atoms in exactly 12 grams of carbon 12. There's a lot of 12s in there. Okay. Again, this kind of goes back again to our atomic mass definition. Remember, our atomic mass definition was also based on carbon 12. So carbon 12 is our kind of baseline definition for things in chemistry. Okay. So ultimately, the question becomes how many atoms are there in 12 grams of carbon 12? And the answer is 6.022 times 10 to the 23rd atoms. Okay. And this is Avogadro's number. Okay. This needs to be memorized and learned and used when necessary, which is not every single problem. And hopefully we'll get some under our belt so we can see how this goes. I'm saying under your belt too much. All right. So this works the same way as, um, oh, excuse me, as a dozen does, right? If you have a mole of helium, that's 6.022 times 10 to the 23rd helium atoms. Right? If you have a mole of water, that's 6.022 times 10 to the 23rd water molecules. If you have a mole of dogs, that's 6.022 times 10 to the 23rd dogs. Okay. All right. If you have, yeah, right. This is only used for counting the number of things. Okay. Um, so there are times when we're going to say like how many atoms are there, how many ions are there, or you have this many atoms, how many grams is that? Okay, then we're going to need Avogadro's number, but we don't always need it for everything. So let's dive into this in a minute here. Okay, so what I want to make a note here is we want to memorize Avogadro's number. Um, there we go, because you won't be given that. All right, now here's another question for you. Right, we talked about atomic mass, so let's think this through. Does a mass of does a dozen bowling balls and a dozen feathers have the same mass? The answer is going to be no, right? Because a feather has a lot less mass than a bowling ball, so a dozen bowling balls has a lot more mass than a dozen feathers. Okay, but there's still 12 of each thing. Okay, this idea is what we're using when we think about molar mass. Okay, molar mass is the mass of one mole of whatever it is you're thinking of. Okay, so for example, uh, and this has been set up nicely for us, right? This is partly why these definitions nest together, so it's a nice way for us to get through it. Okay, atomic mass is the number of particles in AMU. Okay, the mass in AMU is defined on carbon 12. A mole is defined on carbon 12. So we can get to grams of stuff if we think about what the atomic mass is. So here's iridium. Iridium has a mass of 192.217 AMU. Okay. So this would be an atomic mass would be 192.217 AMU. I just want us to get the differences between these things here. AMU. All right. If we want to know what the molar mass is, or what the mass of 1 mole of iridium is, well, it's the same number as the atomic mass, but the units are different. Okay. Molar mass, that's what I'm saying. Molar mass is still 192.217. Okay. But now it's grams per mole. Okay. Atomic mass is AMUs, molar mass is grams per mole, but the number is the same thing. Okay. And this is because they're both defined off of carbon 12. So they link together through carbon 12. All right. This is a conversion factor. And we can use this as a way to get back and forth between grams and stuff and moles of stuff. Okay. And so it's been a little while since we talked about conversion factors, and we often see them written with this slash here. What I want us to remember is that this is, remember the number goes with whatever unit's on top, 192.217 grams for every 1 mole. And then we could also say 1 mole of iridium is 192.217 grams. Okay. Both of those things mean the same thing, and we'll often see this written this way with the slash. So we have to be able to remember that those things go together that way. Okay. If we're needing to count numbers of things, we can include Avogadro's number, right? But Avogadro's number relates to moles, and then moles relates to grams. Okay, so we'll be able to tie those things together like so. And it works in both directions. So we can go from grams to atoms, we can go from atoms to grams, you can stop at moles, you can start at moles, whatever works. We're going to work some examples here, and you'll see a bunch of examples when we get together as well. Okay, let's try this out. All right, how many moles are in 84.7 grams of nickel? Okay, so this is, we're going to get moles, and no, wait, we're not starting with moles. We're starting with grams. That's what we were given, grams, and we're turning it into moles. There's our plan. Okay, we're starting with grams. That was the number that we're given. So 84.7 grams. If you want to put Ni for nickel there, you can, but since it's staying nickel throughout the problem, I'm not going to. It'll keep things neater. Okay, we're going to need molar mass, and we want to set it up in here so the units cancel out. So grams on the bottom, moles on the top, so the grams will cancel. Okay, here's our atomic mass. So this is the number we want. That number is of grams, remember? So this is going to be 58.6934 grams, and that's for 1 mole. Okay, and that's all we need. We got to moles, so one step. We're going to math it out. 84.7 divided by 58.6934 gives me 1.44309240903 moles, because that was excessive. Let's think about significant figures here. There are 6 significant figures in the mass, and there's 3 in the data we were given, so this needs to be 3 significant figures. There's our 3 significant figures. So this should be 1.44 moles. Okay, does that make sense? All right, let's tackle another one of these. How many atoms do we have in 93.136 grams of antimony? Okay, we're gonna do the same kind of idea. Okay, we're gonna have to do an extra step because we're looking for atoms now, remembering that we can't go from grams to atoms directly. We have to go through moles. So we're going to have to go grams at the start to moles to atoms, right? This is going to be our molar mass. This is going to be Avogadro's number. Okay. So start with what we're given to set up the problem. This is the grams of antimony we have. 93136 grams. Again, it's going to stay antimony throughout the problem, so we're not going to We're not going to need to write antimony on every number here. Okay, grams. Okay, grams to moles. We want, so flip my room here. Grams on the bottom, so the grams will cancel out. We'll put moles on the top. This is our atomic mass, so that's the number we want. It'll go with grams. This is 121.76. Okay, and then 1 mole on top. Now, we're going to do Avogadro's number. This is moles going to atoms. Moles has to go on the bottom, and atoms has to go on the top. So the moles cancel out. Okay, Avogadro's number tells us how many things are in 1 mole. So this is 1 mole. And Avogadro's number is, if we remember this, 6.022, I ran out of room, times 10 to the 23rd atoms. Okay. Grams cancel, moles cancel, atoms are there, left over, that's what we got. All right, let's math this out. 93.136 times 6.022 E23. Remember, use the EE button for scientific notation, or you're going to get yourself screwed up. Okay, and then that answer is divided by 121.76. All right, so what did I get? I got 4.606315637 times 10 to the 23rd atoms. We need units in here. Oh, crap. ATOMS. All right. Lastly, we got to figure out significant figures. This dude is 5, this dude is 5, and this dude is 4. So we want 4 significant figures. That puts us there. So this rounds to 4.606 times 10 to the 23rd atoms of antimony. Okay. Sound good? I think I got another one here. What do we got? Okay. A sample contains 9.46 times 10 to the 17th atoms of gold. How many milligrams are in this sample? This is going to have an extra step in it. Okay. Essentially, it's going to be the reverse of what we just did with the antimony problem, because we're going to start with atoms and go to grams. We have to add an extra step in here because some jerk, that's me here, the jerk, wants to know milligrams instead of grams. Okay. So our goal, our plan is atoms to moles with Avogadro's number, to grams using the molar mass, to milligrams using our metric prefixes. Okay. So let's get this started. Here's our atoms, 9.46 times 10 to the 17 atoms. Okay. You can kind of get a ballpark idea in your head as you're thinking through this, right? This is less than a mole because a mole is times 10 to the 23rd. This is only 10 to the 17th. So we should get grams that are less than 196 grams. Okay. Let's see. Remember, we want atoms to cancel. I left myself enough room here. And atoms goes with moles. Avogadro's number is for 1 mole, and Avogadro's number is 6.022 times 10 to the 23rd. Oh, excuse me. All right. Now, we got moles. Okay. Moles to grams. That's our yellow on yellow is not the best way to do that. Okay. But there's our atomic mass, so that's what we're going to do here. We want moles on the bottom and grams on the top, so those cancel out. This number is 196.9665 grams, and that's for 1 mole. Now we're at grams. Okay. We need milligrams though. So do we remember what's our conversion factor for milligrams and grams? Well, grams on the bottom to cancel out. Remember, 1 gram is 1,000 milligrams. All right. Let's math it out. Okay. 9.46 EE17 times 196.9665 times 1,000 divided by 6.022 EE23. Remember, use that EE button. All right. And this should make sense. I'm going to write it over here because we're out of room here. 0.309415987 milligrams. Way too many units here. All right, let's figure out our significant figures. I don't know if we'll be able to see this. This is 3. Oh, that's purple. Huh? We'll leave it. We'll leave it. This is 4, this is 7, and this is exact. So we want 3 significant figures here. That's the 309. Remember, this leading 0 doesn't count. So we can round this dude to 0.309 milligrams. Okay, cool. Let's see, I think I have another one. I do. All right. We have a sphere of pure vanadium that contains 8.25 times 10 to the 23rd atoms. I have no idea how we figured that out, but we got a perfect sphere. We got a number of atoms. We want to know what's the radius of this sphere. Oh, crap. There's a lot of stuff going on here. Let's look at this. All right. So this is the equation for volume of a sphere. We need radius of the sphere as our answer. So that's going to be this R. We'll solve for that. And we have atoms. So somehow we have to get from atoms to volume, and then the volume will give us the radius. Okay, so atoms, using atoms we can get to moles, right? It's the only thing we can't do, Avogadro's number. Okay, from moles we can get to grams given the molar mass, which is here. Oops, I got my circle too big. Here. Okay, and then grams can get us to volume in centimeters cubed, because we have the density. Remember density? Okay, there's density right here. So we've got that. With the volume in hand, we can take this to get to the centimeters for the radius. Okay, it's going to be a little bit of extra stuff in this one, but I think we got it. All right, up to here, we can do dimensional analysis. This last little bit, we're going to need the equation to do that part. Okay, so let's start us off. The beginning of this is just like what we just did. 8.25 times 10 to the 23rd atoms over 1. Okay. We're going from atoms to moles, so we're using Avogadro. Atoms needs to be on the bottom, so it cancels out. We'll put moles on top. Okay. Do you remember Avogadro's number? Oh, I hope so. Ooh, I just made my face disappear. That was interesting. Sorry. 6.022 times 10 to the 23rd. 23rd. I don't know if you can hear him, but there's a loud, hungry kitty behind me. We're almost done. Okay. Blah, blah, blah. That's 1 mole. Okay, did that part. Okay, moles to grams, we need their molar mass. Mole on the bottom, grams on the top. The number here goes with the grams, so that's 50.9415. That's a 9. That's 1 mole. Okay, now we're at grams. Grams to centimeters cubed, we're going to use our density. Remember when we see this, right? 6.099 grams for 1 centimeter cubed. Okay, we want grams on the bottom and centimeter cubed on top. Okay, so our number goes with the grams, 6.099, and that's 1 centimeter cubed. Okay, this will give us the volume. Okay, 8.25 E23. I'm gonna do this in 2 steps, times 50.9415. So this is 4.2026737 times 10 to the 25 divided by 6.022 E23 times 6.099. Okay, 3.672818 times 10 to the 24. This fraction has units of centimeters cubed. Okay, our next step is to divide those two things. Okay, so we're going to take this one and divide it by that one, and I get 11.4426. I'm going to write it over here. So our volume is 11.4426. We'll give it 1 more. Centimeters cubed. All right, that's not where we're done. Let's mark this with sig fig so we can think about that. Use red. This is 3, this is 4, this is 6, this is 4. So we want 3. This needs to have 3 significant figures. Okay, we'll need that later. What we want to do is we now have the volume. We need to calculate the radius. I think I have room for this. So our first step is I'm going to solve this for radius cubed because that's going to be easier. Okay. So radius cubed equals volume times 3/4 and pi on the bottom. Okay. Okay. Once we have that, we have volume. The rest of this is just numbers. So our volume is 11.44264. Even though we know, put the units in there, even though we know that should be 3 significant figures, I'm putting all the digits in there. We're going to multiply this by 3. We're going to divide this by 4 times pi. Okay. So that's our volume times 3. Oops. That's right. Times 3. 34, 3. I might not have enough room for this. 34.32792. And then the bottom is 4 times pi, which is 12.5664 centimeters cubed. Yes, okay. And then those two things divided by each other, that divided by that is 2.73173 centimeters cubed. All right. That's not the radius. That's the radius cubed. We need to uncube the radius, so we have to do the cube root. So the radius is the cube root of 2.73173 centimeters cubed. Okay. Let's see, there's a cube root. Well, it's an n root of the answer is 1.39791 centimeters. Just exactly enough room. All right. And because we know we want 3 significant figures, all these are exact. Well, not the volume, but the volume is 3 significant figures. The numbers here are exact. Let me fix this box. Those are exact. All right. Then this gets rounded to 3 significant figures, which means this is 1.40 centimeters. All righty. This might have been longer, but I wanted to make sure we got some examples down so we can figure this out, right? You can kind of get the idea. We're just throwing a new conversion factor in on us. Okay. If you need me for anything, let me know. We're going to work a bunch of these in class, so we got this.